Narasimhan, and I am in the Department of Material Science, Engineering, and Environmental Science Policy and Management. And I have been coordinating this colloquium series along with Linda, who is the director of the Water Resources Center Archives. And it is my great pleasure to welcome you all today for this semester. This is the fourth and the last colloquium. This is from the field of engineering, where the first one we had was on biology. Professor Rhine spoke. The second one was on public trust in the humanities by Joseph Sachs. The third one was on social sciences institutions by Patrick Wright of CalFed. And this is the fourth talk. Before I introduce the speaker, I wanted to say a couple of words from my own experience as a hydrogeologist who works with natural systems, natural water systems. And it is becoming increasingly clear that as we enter the 21st century, we are now beginning to find that after 200 years of development of resources based on economics since the Industrial Revolution, we have coming to the recognition that our resources in the earth are finite, that we cannot continuously hope to discover new sources of water or energy, nor can we indiscriminately manipulate nature for our own benefit. Sooner or later, the long-term behemoth forces of Mother Nature need to confront us. And in this finite world, it seems Mother Nature has been able to sustain life for 4 billion years or 3.5 billion years by continuous recycling of a very, very small quantity of water and nutrients in some very, very delicate natural recycling system. And it looks like that's where in the future we may have to look into as to how we are going to sustain large populations of the world in a finite natural system. And in regard to water, it looks like we may have to learn from Mother Nature about recycling and reuse of our own precious water. And that's where our today's talk seems to be so appropriate for us. And today we have Professor Takashi Asano from UC Davis and also the Department of Water Resources in California, who has a very distinguished and long career in the area of water recycling and reuse. Professor Asano got his initial training in Sapporo, Japan, where he was born and raised as a young person. Then he came to Berkeley in the 1960s when Berkeley was a very tumultuous and exciting place. He came to UC Berkeley to get a master's degree in sanitary engineering, and believe it or not, he sported very long hair in the true Berkeley fashion. And that's all one of his pictures, the beautiful long hair. Then he went to the University of Michigan, got his PhD in civil engineering, then taught at many places in Montana, in Washington State, UC Davis, and then had a very distinguished long career with the Department of Water Resources in California, where he specialized not only in the technical aspects of water reclamation and reuse, but also in translating that into a series of guidelines and policies which can be used not only in California, but around the world. And his work was recognized all over the world, and his crowning success was earlier this year when he was given the Stockholm Water Prize by the King of Sweden. And that's a very, probably that is the Nobel Prize for our science and our disciplines, and we heartily commend him for that. And he has also been elected a member of the European Academy of Arts and Sciences and many other bodies which deal with water and the environment. And he too, I read his abstract of his talk, and I was very gratified that he also mentioned in his abstract about the importance of responsible engineering in water, wastewater treatment and reuse, when he said that it is very expensive for us to find new sources of water without causing great damage to our environment. So challenge of the 21st century as he sees it in his own profession. He is in the direction of learning to reuse what we have in very judicious ways. So here is, we are very honored today that Professor Takashi Asano is here with us to share his thoughts. Thank you.
Thank you very much. Thank you. I am quite wired here. Here is a microphone, and here is the video camera right there. But good evening, good afternoon, and good evening. And this is a great honor for me to come back to Berkeley. I remember those days in 1963. I was here until 1965. So this was a very memorable period of Berkeley and also United States. And I was just directly from Japan, and I was only 26 years old. So this is a remarkable feeling to come back to Berkeley and to speak in front of you about my profession. So what I like to do though is I realize that I have a couple of those professional friends and who are expert in this area. But I'd like to address this particular lecture to particularly young professionals, graduate student or undergraduate, and or lay person in this area. And so I will refrain to get into this detail of scientific discussions, and if you like, I will be very happy to do that in the discussion session. So let me give you brief idea about what is the water reuse, why we are doing water reuse. So first I'd like to discuss is a concept of sustainable water resources. I think this is a very important theme all over the world. Then I would like to use California as an example, water resources development, particularly in our glorious days of 1950s and 60s. And then I would like to discuss a little bit about drought and dependable water supply issues. And then I'd like to introduce water recycling reuse as an innovative water resource. Then I would like to identify 7 different categories of water reuse with examples. And then I'd like to discuss technical issues and the process reliability. This is a very important issue. And then to touch base with how safe is water reuse, and then to speculate on the future perspectives. And the theme, I think, is I was introduced that all living species in harmony for next century. Now, here is the Time magazine. Nothing is new, but this is the year, this is 1989, January 2nd issue. And remember, Time magazine in every year in the first issue is a man of the year, or a man or woman of the year. But this is 1989, first time this particular picture appeared. And it's quite dramatic that Earth itself is endangered. And of course, the reason for that is the population growth, particularly in the developing countries, and associated water usage. Now, I would like to introduce this particular diagram. This is the one developed by International Water Management Institute. And this is the projected water scarcity in 2025. And what you will see is most of those Mediterranean countries, African countries, and Latin American countries. And presumably, if you use this database here in the International Water Management Institute, there's some 3 billion people in year 2025 is living in our water scarce areas, something like 66% of global population, and the 52 drought countries. One of the difficulty, of course, to use this type of data is if you look at our own United States or Japan or even Europe, you will not see the water shortages as we can see it here. So, but in a global scale, this is a picture they are projecting in year 2025. So, majority of the people, 66% of the global population, will be somehow living in a water-stressed condition. Now, if we look at the United States, and I'm using a little bit older 1980 data, but no difference at this moment, is the water usage in the United States. And this is a USGS database and combined withdrawal of groundwater and surface water. As you can see, that western 17 states uses enormous amount of water, and particularly California. And as you can imagine, the majority of these water use are for irrigation purposes. More likely 70% to 80% of water use are for the irrigation. Now, if we look at California then, to review a little bit about California itself, we have mountains, and that's the Siskiyous, our version of Sierra Nevada mountains, and then Central Valley, and San Francisco, Los Angeles, and San Diego. So this is a basic geography of California. And the idea, of course, is to bring water from north and east to the city of San Francisco, Los Angeles, and San Diego. So this is basically the picture of California, but if you superimpose this on the European map, and this is the one I'd like to really discuss with the European audience, that we are talking about something like we are taking water at the Rhine River, let's say in Germany, bringing water all the way down to Pyrenees, say a border between Spain and France. So this is a kind of infrastructure we developed in the United States, particularly in California. And this is very significant because nowadays, for example, Spain, particularly in Andalusia, that they are trying to bring in the water from Ebro River, very similar to San Francisco Delta, and they try to bring into the Andalusia countries. And also they try to import water from France, along with the TGV. So water would come to Barcelona, for example, Catalonia. And so this is a very big issue, and they really wanted to look at the California picture, what actually happened. So that is the reason I made this particular one. And as you know, we have enormous water delivery systems, plumbing, you like. And water is moved from north to the south, east to the west. And two major aqueducts, the Central Valley Project and also California Aqueduct water plant. Now, this is very significant, particularly when you talk to audiences in a developing country. Now, many new ideas, revolutions are coming in California. For example, such as the water bank, water rights transfer, and others. The actually physically moving water, you need pipelines or reservoirs, and also aqueduct. And many of the countries, they are discussing this new idea, like water banking, water transfer, water rights transfer. They may not have this kind of plumbing system. And this is one area I think California did a wonderful job in the 1950s and 1960s, up to, let's say, 1978 or so. So this is a background of California before we get into this innovative thinking about water banking, water transfer, and so forth. We do have this physical system. Now, obviously, our best water comes from Snowmelt, and this is one of those yellow mountains. And also Shasta dams in the north. Then the water goes through cities of aqueduct. And California is one of the most productive agricultural land, as you know. Some 200 commercial crops, 1/4 of the nation's table foods, 1/2 of fruits and vegetables. So enormous agriculture production. And water is very, very important for the commercial reasons. Now water can be transported all the way to desert, as you can see, like this. So we have enormous infrastructure in the civil engineering, water resources development, and the management. Now let's look at the water picture though in a summary. Let's put ourselves in Los Angeles. Now, as I implied that the water is coming from all the way from north through the Sacramento River Delta all the way to Los Angeles. This is a California aqueduct. And of course, Los Angeles have a Los Angeles aqueduct south of the Yosemite National Park. Then this is our basically interstate international water called a river system. So 3 different surface water lines are coming to Los Angeles. Plus the local precipitation, that's a number 4. And one more is the groundwater locally. So 5 lines, 5 sources of water. And if you look at San Francisco though, we don't have that reliability. So you can imagine how well Los Angeles is prepared for drought, for example, or some disaster. And in addition to that, I'm going to discuss about water reclamation reuse. This is so number 6 water resource. So 6 different water sources are converging to the Los Angeles area. So this is another remarkable water planning. I think whether you realize or not, this is one of the remarkable aspects of California. But despite all of this, undoubtedly we'll face the drought. And this happened in 1976 picture. And obviously city of San Francisco and the Bay Area, it's again enormous population growth. And all of the cities wanting dependable, reliable water, even drought years. So if you look at the Department of Water Resources publications and try to figure out what they are trying to do in the future, this is year 2020. Basically 2 scenarios. One is the normal precipitation year, other drought year scenario. And I mentioned about this drought situation in 1976-77. They had somewhere like a 10.2 million acre feet water shortage that year. And if you look at the normal year in a 2020 scenario, you would find somewhere like a 2.5, 2.4 million acre feet of water will be short. And if it's a drought year, it will be somewhere like a 7 million acre feet. This is the Department of Water Resources projection. They have no really responsible solution to that. So this is an irony of water department, just saying that we have a shortage because of population growth, but we don't have really tangible solution to it. So just for the sake of it, let's remember that 3 million acre feet in the normal year, and 7 million acre feet in a drought year. And I try to match it with the reading through the report that how they are doing it. Okay, remember that the normal average rainfall year, that was about 3 million acre feet. They are projecting that some sort of options in the future, 1.5 million acre feet, and the state water project of some sort in the future, Bay Delta project, CalFed, whatever it is. But they are projecting about 1 million acre feet of reclaimed water. Now this is the picture, let's say roughly about 1/3 of future water supply they are projecting to use reclaimed municipal wastewater. Now if it happened to be a drought year, your picture is more drastic. Remember that drought year they had somewhere like a 7.5 million acre feet shortage. Some sort of demand management, groundwater overdraft. This is the kind of solution, temporary. They may overdraft the groundwater. And this is the one area they're talking about in the CalFed to come up with some sort of options, 2.8 million acre feet, maybe new reservoirs, offstream, and so forth. But reclamation reuse is still there. And I think it is becoming very important. So this is even in our water development agency, such as Department of Water Resources, are realizing this water reuse could be a very, very important, reliable source of water. So with that introduction then, next maybe 20 minutes, I would like to discuss about water use. This is a subject actually I studied for the last 15, 20 years. And I would just like to give you quite a simplistic overview of this issue. Now I think this is a very fashionable, and I think it's correct in terms of thinking about water as cyclic in the system. It could be a global circulation, but if you look at the municipalities and cities, this is a kind of recycling happening. And this particular drawing came from one of the water agencies in Japan, and I thought that was very nicely done. And the focus though, in our case, now this is the global scale of circulation from the precipitation, evaporation, precipitation, and so forth. But what we try to do in a water recycling reuse is to look at the much smaller scale of a municipality. You take water for the drinking water purposes, and then a sewage treatment plant, maybe you're discharging to the environment, where you're recovering that for the purpose of beneficial use, and the industrial reuse, and for the potable reuse, maybe irrigation, groundwater recharge, and so forth. So how small this cycle it would be to be safe, reliable, this is the subject we have to study. But we have a fairly good idea which one is the best choice and so forth. But this is the concept I think we'll be looking at in the future. That the water resources, this is not the discharging or disposing wastewater, but the wastewater can be a resource for the water recycling context. So to look at the benefit of water use, I think water use is an important element of integrated water resource management. And treated effluent is used as a water resource for beneficial purposes. And also, wastewater is kept out of stream, lakes, and beaches, thus reducing pollution of surface water and groundwater. And this is also very important effect of water reuse. Now, if you look at the historic aspect of water use, this is really nothing new. For example, in 1890, Mexico City started to use drainage water to irrigate crops. But unfortunately, this is not a treated effluent. Therefore, public health consequences are rather grave and significant. And our own state, 1912, Golden Gate Park in San Francisco, watering lawns and the ponds. And if you look at the 1926 Grand Canyon National Park, being a water short there, they're using for the toilet flushing in the motels, hotels there. And large industrial reuse happened in 1942. It's a Bethlehem Steel in Baltimore. And this is rather important reuse. Matter of fact, all the steel mill water are coming from a sewage treatment plant in Baltimore. And even now, they're operating it. Very important water resource right there. But in a real sense, modern water reuse happened in the 1960s. First large-scale one is the Urban Ranch Water District in Southern California. This is a planned community of Urban Ranch, and this is the irrigating lawns and golf courses, schoolyard, and playground. Then if you look at the other country, 1969, this is Namibia Windhoek. This is augmentation of potable water. This is one of those classic implementation of indirect potable reuse or direct potable reuse. The demarcation is not that clear because this is the kind of operation they do. And if you look at the other continent, 1969, in Australia, Wagga Wagga started the landscape irrigation. 1977, Dunn Region project, this is the Groundwater Recharge project, just outside of Haifa, Israel. And that water is transported all the way to the Negev desert for food crop irrigation, for example. And I'm going to discuss a little bit about 1984 Tokyo government toilet flushing installations. And I do quite a bit of work in the Mediterranean countries. And this one example I'd like to give is 1989 in Costa Brava. This is north of Barcelona, Spain. Golf course irrigation with a tertiary treated effluent. So water reuse, in a sense that the modern water reuse started from 1960s and going over almost all of the places, including Middle East, Saudi Arabia, Arab Emirates, Kuwait, and so forth. So with that in mind, I'd like to identify 7 different categories of water reuse: agricultural irrigation, landscape irrigation, industrial reuse, groundwater recharge, recreational and environmental, non-portable urban reuses, and finally, possible portable reuse. Now this is an example. This is just outside of Fairfield, Suisun area, typical irrigation. And this is a turf company, nitrogen and phosphorus in water, wastewater, so it's a very good water for them. And this is my favorite picture, that irrigation in a cemetery, nobody is complaining about it, or dead, but beautiful flowers, nitrogen and the phosphorus, and irrigated with the reclaimed water. The next category is the industrial reuse. Can be cooling water, boiler feed, processed water, and the heavy construction like a dust control. And I'd like to just concentrate on this cooling water because this is a rather significant use of water in any kind of industry. And one of the difficulties of industrial water processing is that a variety of processes, and it's very difficult to control. But cooling tower, this happened to be in a Burbank area, Burbank Water and Power, is that this cooling tower is a basically separated unit process. So you can get in and you have a same kind of water quality anywhere, refineries, city, power generation. And this is a very good application. And usually it could be a secondary effluent, well disinfected, or tertiary effluent is more common. Now, next topic is a groundwater recharge. This could be groundwater replenishment, saltwater intrusion barrier, and subsidence control. The concept of groundwater recharge is a fairly simple one. That you have water treatment, cities, and wastewater, maybe advanced waste treatment, and treated effluent is put into the ground by way of surface spreading or maybe direct injection to aquifers. Then water retains stayed in the groundwater for a couple of months to years, then bringing up, pumping. So what happened basically then up to this point, it's probably still sewer water, if newspaper people would get into that. But for us it would be reclaimed water. But going through the BADOS zone, unsaturated zone, or well treated here, that this would become the groundwater. So I think psychological transformation of sewer water to groundwater is very important because they stay in the ground for, say, many years. Or public health implication is also very significant because all of the pathogens, some toxic chemicals may be retained, decayed through the ground system, unsaturated zone, and also in a saturated zone. So groundwater recharge is a very important concept, fairly simplistic, but the issues are very complex. So I took this is the classic, say, sanitary engineering unit processes. But this is operated in Orange County Water Factory 21, Orange County Water District. This is already since 1976, almost 21 years of operation, 21 million cubic meters, 50 million gallons per day, and no more than 5% of reclaimed water actually comprise the domestic supply. So this is the way they are treating it. And I will tell you a little bit about more recent development. But the classic environmental engineering, sanitary engineering unit process, lime, clarification, decarbonation, filtration, split into activated carbon treatment, and also reverse osmosis, and the chlorine disinfection, and the deep well disinfection, injection. Now, the most recent scheme would be more likely secondary treated effluent and going through the microfiltration reverse osmosis membrane system. This is going to become standard in the next couple of years, particularly with respect to groundwater recharge. Now, this is right after the lime clarification. This is again Orange County Water Factory 21. Sewage water looks like this already, very clean, sparkling looking. And that goes through the reverse osmosis membrane, typically looking like this. And then directly injected into 4 different aquifers. Now, this scheme though is a little bit misleading in a sense. We want to call it, this is a seawater intrusion barrier. Now, this is a very good way to get the permit to do it, but the reality of this is about 80% of water is going inland because somebody is pumping it in the inland. So about 20% goes this way to stop the intrusion, 80% goes into inland somewhere. Okay, so that is the scheme. And it seems we are going to talk about public perception. No doubt, I think we will have a discussion on this. But if you say this is a seawater intrusion barrier project, that means simply stopping seawater to coming in and contaminating freshwater aquifer, permit would be issued much easier than saying that this is indirect potable reuse because you're drinking this water somewhere. So this is one discussion I'd like to have with you after this presentation. The next one is another recent development, recreational and environment, lakes and pond, marsh enhancement, wetland is a very big issue. Stream flow augmentation, fisheries, very often in Asian countries, they're using reclaimed water for fish hatcheries, for example. Snow making, not the yellow snow, okay, white snow. Don't eat that yellow snow. Okay, example, this is Los Angeles, city of Los Angeles, Tillman water reclamation plant. They made a Japanese garden out of this. And this is a Japanese garden, they say, but this is a Chinese writing. So, you know, this is Oriental feeling about it. But this is a beautiful one, eh? All the crops and trees. As a matter of fact, this is the best place to get married. Lots of weddings are taking place here. The sewage pond. Okay? But water is short in Los Angeles. And I think this is the purest, cleanest water river in Japan. And obviously children can wade and play. But this is coming from a sewage treatment plant. And this is one of the demonstration projects in the Tokyo metropolitan government. Reverse osmosis and ozonation and this. And I'll show you where this is coming from, okay? But this is the cleanest water in Japan. Now, next one is a non-portable urban uses, fire protection, air conditioning, toilet flushing. And I like to deal with this toilet flushing in the metropolitan areas. This example is in the Orange County. And this is a new building, and it's a dual plumbed, two plumbing system in it. And I was lucky enough to get in there when they are building it. And one, of course, is a drinking water pipe. And the purple pipe is the reclaimed water. This is a fairly standardized now, originated from California, but all over the United States nowadays, purple line is a reclaimed water. And in addition to that, this is the earlier days of experiment, demonstration. So they went, in addition to that, purple tape. So this would be behind the wall, so plumber can get in there. Just simply touching it, you would know exactly what the pipe you're talking about. So this was a very careful to prevent the cross connection, connecting two lines here by accident. So this is a major issue for this type of application. And I would like to discuss a little bit about this Tokyo, downtown. Okay, remember that the water is short in the future, population growth, all of that, but here it is. Now, most of those cities in Tokyo are built right after the war, a very hasty way. And they had to renovate old sections with more high density buildings. There's no way to bring in the water here. So what happened, and also a sewage treatment plant, is this. This is used to be a water treatment plant right here. And they built the sewage treatment plant underground. And that cleanest water children were playing was right at here. And the surface is that's the office building, tennis court, playground. And the water here, wastewater treated, is transported to these buildings, these 19 buildings, including Hilton Hotel and others. So this is about 2.5 kilometers. And this water is used for the toilet flushing. And here are the examples. This is the City Hall, Tokyo Metropolitan Government. And all commercial buildings are all dual plumbing for the toilet flushing. And it is an expensive enterprise, but there is no way to bring in water, big pipelines digging up all of the places. So this is almost now 15 years since that happened. Now the next one is ultimately we get into this discussion, whether you like it or not, is a portable reuse. Blending in water supply or pipe-to-pipe water supply. And I just have one picture, which I got the permission, good friend of mine, demonstrating for you drinking reclaimed water. This, by the way, is just only tertiary treatment, and I was the one taking this, and a good friend of mine. And he's still alive, so I think Bioassay is okay. This is almost 10 years old now. This is a heavily chlorinated tertiary effluent. And obviously, when you talk about Orange County, that is the membrane treatment, reverse osmosis, so water quality is much better than this. But he's still alive. Okay. Next, undoubtedly, when you get into this kind of picture, then we have to discuss about how safe is water use. And we have to get into this argument of acceptable health risk debate. Should it be absolute risk, or should it be relative risk compared to something? Should it be zero risk, or should you have some acceptable risk for this kind of operation? And that relates to microbiological risk assessment, particularly in case in the developed world, Europe, Germany. I happen to be with the European Union program with them now, is the enteric virus issue, and particularly with respect to treatment. And regulatory oversight, monitoring issues, enforcement, and others. And another one, I think it's becoming very important in the recent years, particularly with respect to indirect portable reuse, such as groundwater recharge, is a chemical exposure risk assessment. So those are the issues I think we have to face in the future. And we'd like to get into some discussions with you after this. Just want to entertain you a little bit of this peanut butter is toxic, lasagna. And I just want to give you some history of this. This MTV, somebody is studying that.
Those rats.
NDMA. And nitrates in the drinking water, groundwater. And this is a good one, I think. Is in the campus, aphrodisiac is very important and very dangerous. And everything could be very dangerous. Now, this is the one topic I think we should discuss a little bit later. But what basically is happening is this. This is, by the way, coming from National Research Council publication 1986, that most of our study, what we are talking about, is in terms of exposure assessment, we're talking about percent or parts per million or milligram per liter range. And we are talking about 1 out of 100, 1 out of 10, something like that. But when you discuss this public perception and the zero risk, we are talking about parts per billion, parts per trillion range. And we are talking about 1 out of 100,000 excess risk or elevated risk. And this is the concern we have. But what the science can tell us is still in this area, which we are talking about percent or parts per million. Now this is a dilemma we are going to get into when we talk about the water use in a very intimate way, such as indirect portable reuse. So I think this is a kind of thing we have to deal with, that you have some dreadful sewage molecule somewhere, one molecule in one grapes, or something like that. Is that safe? This kind of argument. And so what I'd like to discuss then is just about time now, is to look at this in an entire spectrum. I take some water quality parameters. This could be anything, pH, suspended salt, BOD, some toxic chemicals, nitrates. And presumably you have unpolluted source of water, pristine water. And, but it's not good enough, so we elevate water quality by water treatment, and we reach some water quality such as this, meeting EPA's standard or California drinking water standards. Then after that, obviously, we generate the wastewater or sewage, so water quality is down here. Now, in order to discharge or dispose this wastewater, we had to do treatment. And this is the one we started in the 1960s and 70s when I was here, wastewater treatment, and safely discharge to environment, receiving waters, estuaries, or ocean disposal. But since this requirements for treatment is much, much higher than used to be, like a primary treatment, secondary treatment, if you put a little bit more money into that, it could be reclaimed water. And that is the turning point, I think, that once you call this is no longer disposed or discharged and becoming reclaimed water, water resources, you would generate the economic value to it. This is a part of water resources, element of water resource management. And I think this transformation is very important. It's a very simplistic approach, but this happened, as I mentioned, in the 1960s. And particularly last couple of years, we are getting into much higher treatment, like a membrane treatment, advanced oxidation, very sophisticated disinfection, so that it would be much higher water quality, maybe higher than drinking water standards. So conveniently, this I can quote City of San Diego case. They call this to be depurified water, whatever it is, but depurified water, meaning this water is a very, very high quality water, and maybe equivalent to or higher than drinking water. Now the argument is, should you drink this water or not? This is a discussion. Okay, so this is the one example I would like to give you outside of California. This is the El Paso, Texas Groundwater Recharge for last 25 years. And this is the activated carbon treatment, reverse osmosis, and ozonation, and the groundwater recharge. So I borrowed this from DuPont's advertisement, but the idea, I think, is we had to live in harmony. And this is a permeator advertisement. And we are living in harmony with the nature, and we have to share the water resources with other species. And with that, then certainly we can maintain beautiful environment for next generation. And that is my the formal part of presentation. Very easy, no-brainers. But at least I hope you would understand where water use is coming into and where we are heading for, what the research topics are very important. And by nature, water use is very much of interdisciplinary, not only science alone, but economics, political science, sociology, all of that. I think it is an enormous challenge if you go beyond irrigation of crops, landscape, and maybe wetland and so forth. But once you go into this area of the water resources, in a sense closer to drinking water issues, then also you can argue then what is different here in unplanned incidental water use, such as in Mississippi or Ohio River or any other polluted rivers and streams. So with that, I would like to thank you very much for your attention. And this is the formal part of very broad, simplistic way of looking at the water use. Thank you very much.
We have plenty of time for questions, comments, and discussions.
First, let me thank you
Yes.
for giving us a lot to think about here. is to start with your last slide. From a biological perspective, I'm worried you started with what you call unpolluted water. Many of us who are concerned there is no such thing anymore.
That is true.
We're showing that what we think is unpolluted water is very hard to find true unpolluted water. And one might well argue that a lot of the even lower reclaimed water may be better quality than what we're starting with in the beginning.
May I address that particular issue with all respect? This obviously we are scientists, engineers, well educated. But now though the perception in the public is quite different. Now remember I showed you the snowmelt in the Sierra Mountains. That is where they are looking at. So where do we go? We go to snowflakes. Okay, then you can argue even Alaska or North Pole, you have all sort of trace elements right there in the snow. But the public is different. And this is traditionally though, in environmental, I think I use the old term, sanitary engineering practice, that always we seek the pristine, unpolluted water for source of water. And that is the principle of public health engineering. And as a matter of fact, I studied that in the 1960s here. And that was an illusion maybe, but at least that is our ultimate goal, to try to find the best source of water available. Now, we can argue that, yes, if you look at the GCMS, what is that purity? But in a public, I think, though, that is a very important. Now, this is a difficulty we're going to face when you try to communicate with the public, and including newspaper. Today, we have a newspaper from San Francisco. I think we, as scientists, engineer, we can talk about, no pristine, no pure water exists on Earth. But at least in a perception-wise, let me say, we have somewhere, this is a pristine water here. We hope that is maybe snowmelt.
I think it was a slide maybe immediately before this that showed risk versus...
Let's go back, yes. Yes, definitely.
Okay. Now, what I get a bit lost in that because I didn't know, for one thing, are the PPT through percent, are those exposures as percentage of recycled water, or are they contaminants within the recycled?
No, this meant to be, this was the academic science study. Yeah. And I happen to be part of this study. This is the water management in the coastal urban areas. This is water resources management in the coastal urban areas. That was a report. And what they meant was a very simplistic way that we are talking about, when you talk about concentration of something, chemicals A, we are talking about percent or parts per million.
And the risk is a risk of something.
Yeah, and we are talking about, when we talk about clinical observations, we're just simply talking about, what you can detect is like 1 out of 10 elevated case, or 1 out of 100. That is all what they meant. It's no really direct correlation for that, just to try to illustrate some of the accuracy or roughness of argument.
Where does recycled water fit in this whole thing we're talking about directly?
Well, now in case of like Los Angeles, this is a county sanitation district, Los Angeles County. They have been doing this groundwater recharge in the Whittier Narrows groundwater recharge site. They have done 2 different epidemiological studies, and they could not find any correlation with any kind of elevated cases, cancer, rectal cancer, and so forth. Yeah, right. So I think we are really talking about this kind of accuracy, but our concern is all here, like a newspaper, articles, we are concerned. Could you, anybody? Yes?
Well, yeah, most of the examples gave generally are fairly large scale, you know, the example of Tokyo or, you know, lots of ones that I'm familiar with. You also hear a lot about kind of, you know, much smaller scale, you know, gray water recycling at the home level, and then this idea of kind of a neighborhood treatment plant. And this is common kind of where you see, are we talking about two different kind of philosophies of reclamation, or do you see them integrated together, and kind of get your opinion on those small scale, you know, individual units, neighborhood units versus the large scale?
What I would like to say about that is basically what I presented to you is a water use in the scale like a publicly owned wastewater treatment. That means a municipal system. Now, if you get into individual house gray water recycling, I think it's a different story. You don't have any monitoring requirement like what we have. You may be doing it for your vegetable garden and so forth. And I do not know really well enough to say anything about the individual ones, but I do know some the system like in Arizona.
I'm wondering though, as part of an urban system, instead of looking at these massive, you know, bringing in the sewage and areas, doing kind of neighborhood scale mini treatment.
That is I think a future picture of that. It's more like a satellite plant.
Right.
And you can, what they call it, sewage harvesting or whatever they call it. Just you can take out water as much as you want from sewer lines and go through the membrane system and use it locally in a district. And then a sludge can be sent back to the sewer lines. And this system, though, system is large enough, is Los Angeles is doing that. It's very similar to that in upstream treatment plant, like San Jose Creek or Pomona, all doing that local recycling, and then a sewage sludge would be treated in a terminal island, for example. So, but that scale is too big. I think what we are talking about more is a little bit smaller scale, and for the sake of local water balance. And, but always though, this microbiological issues, bacterial issues, adequate disinfection would be a major issue, or the safety of it.
If 80% of the water utilization is for agriculture, what are the strategies for recycling and that water? That would seem to be where you really want to make the greatest conservation.
Yes.
What are alternative strategies there?
So far, this agricultural irrigation is done very well, almost all of the places. And but the one thing you have to be very careful about agriculture is a kind of agricultural water you are getting could be like a $50 per acre foot up to about $250 per acre foot. Now, these water, if they are already treating tertiary and the safety use, it maybe you can make it like a 250, but the more recent ones are much more expensive. So therefore, it's more likely $500 acre foot, okay? But you can talking about $900 for the future increment of water, $1,200. So you have a place to go, but the traditional agricultural reuse in California are done already, pretty much. And it could be a disposal option, like some of the situation like Fresno, for example. But pretty much in a range when you talk about $50 to $200 per acre foot water picture, it's already done. So what you are seeing it in a growth industry, if you are investing on it, will be landscape irrigation, golf courses. Now they spend enormous amount of money for greens, and they don't want to lose green even in a drought year. So they decided to keep golf course green, and they are going to buy water, let's say $700 acre foot. And that is where growth market would be.
There's actually though one area I'm working in extensively where in agriculture in Central Valley, you got a drain problem with the salt accumulation. And it's an issue they're trying to tackle with reverse osmosis plants as a way of solving the selenium in drainage water. But there are technological problems. I wonder if you could comment on that. The technological problem we're running into is the hardness. The reverse osmosis is clogging up. Do you think that's a solvable problem?
May I ask one question on that? Now, is agriculture in San Joaquin Valley sustainable?
Personally, I don't think it is. In the next our lifetime, it is. But.
See, professor can ask questions to the student. But now, this is argument, you have to get into that. But now, yes, technology is there, but desalting somewhere, if you maintain agriculture in the desert, you have to intervene somewhere in the salt or TDS, whatever it is. And then your argument would be, is that sustainable? So would it be better to buy alfalfa from Nebraska rather than growing alfalfa in the desert? This is the kind of argument that we have to get into, and the water use is no different. I think it is a very violent discussion. I mean, water, if you bring in water, it's growth inducing. Nobody wants to have a growth. And you are familiar with that in Dublin San Ramon, for example. With that challenge, you can always argue, because this is Berkeley, remember? We had to argue. Yes, David.
Following up on that question, I think we could make up our water excess in California if we eliminated farming of sort of low-value crops, like alfalfa, you said. And my question is, as scientists, are we being irresponsible by continuing to investigate the health risks and leading people down this kind of black hole of questions that we can't answer? And should we at some point just say, the logical answer is in front of you, we should even pursue this science anymore?
Do you have any opinion on that? You're a consulting engineer, I gather.
No, I'm a hydrologist. I don't claim to be. I'm an earth scientist, so I'm a water manager.
Is there any consulting engineers here? Well, no. Okay. But I think, well, remember, we are sort of academician in a way. But I face lots of those discussions, and with a very compassionate discussions. Obviously, agriculture is a heart of American democracy even. And I think we have to be very sympathetic about that. But at the same time, we have to discuss, argue, is it sustainable? And what do you do about the salt? Selenium, if you like, yes.
But it isn't, we got to also get beyond stereotypes. I just spent the whole day with a farmer from Wessex, last 2 days. Very progressive, open-minded farmer. He's got, he's in a drainage impact area. He's not growing alfalfa. He's making money growing tree crops, tomatoes, lettuce. He's growing, and he's got an innovative where he's taking his rainwater and putting it on, it's getting saltier and saltier and growing more and more salt-tolerant crops. And then he gets a commercial salt product.
Sure.
So there is, I think, room for, creative minds to work with that. He also has some algae working on it too, and so, but there is, the basic question you asked about, sustainability of that kind of agriculture. I think in the long term it isn't, but there is a room for technology, I think, to give us, at least in the next 50 years, some solutions if we're going to get through our environmental.
Yeah, that's true. That's true. Yes.
I didn't want to crowd out a very stimulating subject, but we're at the other end of the problem where we have to provide potable water as a utility. And right now, I guess you well know, arsenic has suddenly become one of the big dominant questions. And we sought advice, and I'll get to my question in a minute, but we sought legal advice. We got 2 firms because we were so concerned if we could get a consistent opinion. What is the liability exposure as a purveyor of potable water when you get to levels, let's say, the MCL, which I understand now is going to be 10 parts per billion, but much lower levels that epidemiological studies indicate. And so you have a double standard. Which one do you treat to? You rush in and spend a great deal of money and maybe be wrong.
Right.
I'm curious now about reclaimed water. In that discussion, they said that food, when you start to get to 10 parts and below, becomes a significant factor for arsenic. Is that, first of all, of any significance as it goes through the reclaimed water treatment as far as just arsenic is concerned? Is it going to be removed economically? I'm sure it could be removed. But is it going to be removed cost effectively?
I'm not sure.
We worry about it because
Sure,
if it recycles back to the aquifers, then the problem's passed on to
Not to be true.
conveyors.
Yes.
And maybe at parts per trillion instead of parts per billion. And it's a huge economic swing,
Right.
and ultimately the customers will pay for it. And so right now, it's just a very big current question.
Right.
I just want to underline it and leave it as a question.
Yeah. David, do you have any opinion on that?
I think you hit the nail on the head that we can't, like your slide shows here, we really can't say with any certainty with risk assessment whether these low levels will have an effect. And then it's an insoluble problem at this point. And that's why I think that we have some responsibility to say that our science may not be able to resolve this issue. And that was the question I was trying to pose. At some point, we're meeting public health agencies down an alley that would be much more effective saying maybe this is a crazy idea to pursue indirect or direct programs.
There's one add-on to this remark, I think, that is under consideration. It's how serious the question is. That we serve approximately 1/300 of the water we serve is for drinking. It's very small, a couple of gallons
Right.
a day, a family typically, something in that nature. If the law would allow it, it doesn't now. Potable water, bottled water, has to meet certain requirements regardless. So you have to treat all this huge quantity of water to water the lawns, to put out the fires, to flush the toilets. Whereas, and there are some units now that are actually looking interesting, right at the house level, almost plug in the wall, little distill units, will make potable water.
Just before we get into that, I know my friends wanted to do color. You're here, but the couple of issues though. Now, where do we go from here in a water use? Are you going to drink sewage water? Now, this is a very ugly picture. The newspaper people put, for example, rich people's sewage, poor people's drinking water, or toilet to tap, all of that. But I think in case of California, knowing this technological development and alternative energy and so forth, desalting will become very important. And if that is the case, then they can treat very small amount of water and high quality water, stainless steel pipe maybe, glass pipe if you like. That kind of technology would come in. But that would not be agricultural use, like a desalting in agriculture, but pure drinking water. This is a safe, reliable source. That could be the one solution. And I think technology is such now, you can talk about what, $650 per acre foot, closer to power generation, intake and others, up to $1,000 per acre foot, desalting, brackish water.
MWD is delivering.
They are about 550? Yeah,
$1 an acre.
something like that. So this is a very interesting area. Now, traditionally, water resource engineer, we poo-pooed about the desalting until maybe 15 years ago. But I think it's becoming an interesting quality. Now, one thing though, here we are number 7 economic power, number 6, and it's bigger than France now. Okay, so we are talking about this kind of technology, rich people's technology. Now, you are immediately challenged here. Berkeley became very mild nowadays. Nobody challenged me yet, but different from 60s, I guess. immediately they would challenge you. Well, you talk about this, but what is the consequence of not having water at all? What is the consequence in the public health? Now, I am advisor to World Health Organization, Geneva. Now, this is an issue. What happened? You guys are coming up with a very stringent requirement for WHO, but what happened if you cannot meet that? You say, well, you're a second-class citizen, so you are okay with that? Now, how would you handle that? Yes.
You bring up, the whole idea of challenging bringing potable water to 2/3 of the world that doesn't have it. Isn't what we learned from this rich people's technology actually very applicable to the extent that they don't have that clean, fresh snowmelt as they have the polluted water? So isn't the technology that we've developed here for reclaimed water, we can downscale it, make it affordable, then make that unpotable water potable for them. So there is some technology transfer. The challenge is how to make that affordable to the 2/3 of the world that doesn't have it.
And until now, the easy way out on that issue was that you say, hey, we are making this high quality water. We call it Title 22 water in California. It's good for vegetables, salad crops eaten uncooked. This is the way. But they try to eliminate this chain of transmission of pathogens by restricting crop you can apply, or you are restricting people to be exposed. That is the way traditionally they did it. And your treatment could be lagoons, pond. And that is the way you did it. But they are talking about, obviously, not the enteric virus like what we are talking about. It would be helminth egg. How many helminth egg can you count? And that is the situation, because it's a different level of sanitation, let's say, or health delivery system. Yes, please.
I served on the EPA Science Advisory Board. So we discussed the issues, and I actually was responsible for putting in the reports the language about EPA seeing whether we could do something differently for small systems, because in that case, the real issue is small systems. The cost of treatment is, there are substantial economies of scale. In South San Francisco, LA, Albuquerque, basically the costs, I think, about when you get to small communities, under 250 or anything, enormous. Now, and so the issue was really, could you have a differential standard for small communities? The political objections were, how can you say that people in a small city can drink arsenic and people in Albuquerque don't? But this is the point I want to make. The big obstacle, from my perspective as an economist, is the plumbing. Most of the water in the United States, nobody pays for water. You pay for plumbing. Nobody pays to get the raw water, and like say electricity. It's all the conveyance. And the problem with reclaimed water in a large city is you need to get the water from the treatment plant to where it can be used. And groundwater injection is fine because you can inject, but for other uses, unless they happen to be close to the treatment plant, the plumbing kills you. And that's partly. Now, in the small systems, just with the arsenic, the notion of distributing, the notion there of dual use, where you just a water utility in the small system just gives bottled water to people, and the distributing it is straightforward and is cost. The problem is in LA or San Francisco or whatever, distributing bottled water is costly. Not impossible, but it gets to Peter's question earlier about the scale of things. It's a matter of matching the water source to the water use in such a way that you keep the plumbing costs down. Yeah. So in a sense, it's not the treatment, although there'll be wonderful developments in treatment. But in some sense, the thing you have to still overcome is the arranging so that the transportation, the conveyance costs concern.
Yes, Asano.
I want to first respond to David's question about whether we are irresponsible because we want to know. And I think my answer is we must know and we will know. Otherwise, we will slide into an abyss of uninformed decisions. And that's not bringing anybody any benefit. But I think we are also missing a few other points. And it was alluded in your statement about different treatment for different people. Water has this, I don't know, mystical quantities or religious or quasi-religious characteristics for many people, both on an individual level where people do not mind putting known poisons into their bodies like alcohol, nicotine, or nitrosamines, and yet they're gonna fret about parts per trillion for their dogs. On a social level, a society level, it's very similar. I have friends from British Columbia who will gladly sell us apples that are possibly labeled Alar, but ask them about selling us their pristine water, quote unquote pristine water. I think this is a very important issue that economic analysis is, that people, especially in affluent societies, strangely enough, feel that they need or they have to pay for good quality of water, whether they're getting or not. Maybe it's just a matter of spending money to make them happy. I don't know, that's a very important thought.
So just one, that's a very relevant remark, I think. But I alluded to the legal problem, the double standard, and providers are in serious legal jeopardy. And that's been consistent advice from many law firms right now, as to which standard they treat, the MCL, or you might call it the ethical standard, wherever that may be. And it's kind of a scale of risk, and it's a very serious risk to purveyors, whether they're public or private. And it's a dangerous problem.
Bob or Rick, you want to say something?
Well, I mean, private water companies particularly face that problem because they can be sued by the public if they're not providing perfectly safe water. So we set the maximum contaminant level, the legally enforceable level. It's something that's feasible and has a good cost-benefit ratio. And in case of arsenic, the risk is going to be, 5 times 10 to the minus 6, something like that. Whereas the published public health goal, if we were to come out with one, which has to be set at the 10 to the minus 6 risk level, de minimis risk, that's going to be 2 parts risk. We don't know yet.
But there's actually tort law firms right now that are taking copious notes and preparing for much more levels than the MCL.
Yeah, and so private companies, I mean, public companies can be sued over that. Private ones can't, which is a real disadvantage. And I don't know what you need for it. What you treat for. I think it's more of a legal issue than a public health issue.
But yeah, in case this Bob Harkist from Department of Health Services, State of California. Nick, you have anything?
No, any thoughts at all.
Okay. Kara, you have anything to say? Good to see you.
I guess relevant talk that I'm having that's different from what anyone else is saying is that it's just important always to remember the kind of message that we send to the rest of the world. And as an example of that, there are a number of people, or there was a time in the late 80s, early 90s when this sort of scare went through all of Latin America, where the results about the health effects of disinfection byproducts were coming out and making big splashes in the news. And so everyone in Latin America started worrying about dying from disinfection byproducts, and the majority of the population doesn't even have access to chlorinated drinking water. And they actually were people talking about whether it was safe to chlorinate drinking water in Latin America, and which is totally preposterous. And the number of lives that were saved by overdosing water we might save by keeping the levels of disinfection by it's very low, by maybe using no disinfection at all. So, I don't know, it's just always important to take a step back and look at what we're really talking about. And I'm curious with the evaluation of the legal standards that's going on with the European Union, and you're working with the World Health Organization as well, right?
Yeah.
Are those standards going to become much more strict?
We are not getting into that much yet. This just bureaucratic rearranging that kind of a system. Now we are waiting for a budget. I think European Union wants something, WHO want to have something. But
because the World Health Organization standards for reuse are orders of magnitude strict.
Right. And then another issue, though, I think is very important, is process reliability. Now, they often take California standard and say coliform, total coliform, 2.2 per 100 milliliter. And they put it in there. But we do know why we have that, because we have certain reliability in the process and the performance. But if you don't have that, and say 2.2 per 100 milliliter, it doesn't mean anything. How do you protect public health? Those are all unknown. And then this is a very dangerous, like taking California standard in developing countries, for example.
I think you were alluding in your talk about one of the fundamental challenge of reuse, and what you get onto is this perception of the toilet tap, the perception that people demand that they have this clean water, even though bottled water, taking bottled water as an example, the standards, the regulation on bottled water is much less than on public water, and so it's all about marketing. So maybe we should learn from the marketers. Let's take the reclaimed water, put it into the bottles, and sell it as pure, pristine bottled water, and there won't be a problem, right? Then we've solved the problem that way. I mean, it really comes down to those incredible, weird, incongruities people have about the perception of what they're getting.
Yes, Carla.
The advertising agents that are advertising the bottled water and get them to advertise municipal water, so people have more success.
I should say bottle it.
I just wanted to.
What happened to this one?
I just wanted to make a final comment. That is, all this public perception and everything is finally linked up to education. And we have been pampered in the past by a feeling of as if we are living in an infinite world and that we could have anything and everything we want. And we have essentially a confrontational system where anybody can sue anybody else for any amount of money. And that is now gradually changing to a situation that we are all coming together now. No one group is going to make decisions. And we are becoming more and more conciliatory in making our decisions. That learning process is going to take some time. You are absolutely right. I have never in 30 years in California felt any need to take any water other than just take it off the faucet and drink that water. I am very healthy, thank you. And I see people like pacifiers carrying bottles around, paying $2 for a bottle of water here. And that water is not as regulated as this, but still there is a public perception. So I think eventually things will change because the boundary conditions and the uncertainty of the natural system will eventually get us, I suppose, and bring us to some kind of a size and shape. Thank you very much, sir.
Thank you. Thank you very much. Thank you.